at 0, the value is what we know, is n0, 87.75. 87.75 at 1, it's 40.9. The 2 is 19, you see, 19, 18, 40, 49. You know there was this difference there, because it's a probabilistic matter. 19.07. And the other one, let me get a decimal more, 40.99. And then 1, 2, 3, day 3, 8.89. The value, experimental value is 7, the predicted is 8.89, small difference. 4.15, and the experimental is 4. Fifth day, 1.93, and the value is 2, the predicted is 2, and 0.90, and the experimental was 1. And the 7th day, 8th day, is when it's less. So this is 0.52, we don't have experimental value because it stopped. The experiment stopped. So why are we doing all this? Because we have the experimental data. Yes, we have the prediction using probabilistics. Yes, but why do we want to do the equation? Yeah, because in science, this equation tells the story of the samurai. How many samurai were at the beginning, and I forgot the time there. Time is the number of days. Okay, it tells the story. In this case, it's okay because we have all data, but using the equation, we have the whole phenomenon. We can able to predict intermediate values. I'll give you another example, not now, so you can see how this can be used to predict what is going to happen. In this case, it's not necessary. Yeah, but science is something like that. Gauss was curious about what was the equation that described the full phenomenon. Besides the probabilistic, it was not really an equation. Yeah, but it was very simple, right? Like number, and then every time the 0.5, right? Of the 50%. He wanted to know if we could find an equation, and he developed the tool, so it was able to tell the story using an equation. And then once the least square minimization was developed and published and everybody knew about it, scientists started to using it, and we still use it today because it's a very simple way to convert an experiment into a learning and an equation that we can use, right? And then from a mathematical point, it stops there. But remember that I told you that in physics every coefficient must have a physical meaning, right? So the x is the time, the y is the number of samurai. Running out of time. But the first coefficient should be very close or equal to the initial number of samurai, and this coefficient is related to, I told you, the number, the rhythm at which samurais die. So it's related. There was a relationship between this and the 50% of every toss in a coin being alive. So with that, it is not enough to understand the full power of least square minimization, but at least we introduce it and how Gauss got to that idea. So we will develop it in future videos. We have to remember as a final is that it's so important that it is implemented in every scientific calculator. Okay, so see you soon when prepare and show you an experiment where we can use it to explain and to predict what is going to happen. It is really interesting. Okay, bye.